One of the really big ideas in calculus is this concept that maybe we've got some function graphed. And let's go ahead and give our, ooh, that is not a straight line. This is some squirrely graphs we can manage. So if you have a function in mind, maybe you want to know what the area is underneath that function. So maybe from this endpoint on the left all the way up to this endpoint on the right, we might want to know what is the area underneath the curve above the x-axis between these x equals a, x equals b boundaries. And what the first idea to address this is something called Riemann sums. What Riemann sums do is they take your independent variable axes, so that's the x-axis, and they chop it up into intervals. And then from there, they take each of those little values. So if x is a at this left endpoint, the next endpoint, let's call it like x sub 1, then x sub 2, x sub 3, x sub 4, x sub 5, and then the last one would be x sub 6 or x equals b. So we chop up our interval, the x interval, into these small little subintervals. And then we take each one of these x values with the little subscripts, plug them into our function to figure out where they would land on the curve. So that green dot on our curve is f with x sub 1 plugged into it. We'll do the same thing with x sub 2. Same thing with x sub 3, x sub 4, x sub 5, x sub 6. And then from there we would create rectangles using those points on our function. And this can be done in different ways. I'm going to choose to use a left endpoint, which means I'm going to use that function value to create a rectangle where the function value is the left top corner of my rectangle. And then I'm just going to create a bunch of rectangles using the subintervals on the x-axis and the function value as the left endpoint of my rectangle. And once I have all of these rectangles, I can calculate the areas of those very easily, because remember that area of a rectangle is just base times height, or length times width. So we'll calculate area of each rectangle. Basically by using the space between the x values, that little subinterval, and the height of our function at that left endpoint. So we have height and we have our base. So our base is whatever the space is between these x values. Let's call that delta x. And our height comes from the function with that the left endpoint. Ooh, I said left this whole time and it's right. This goes to show you how spent I am at this point. All right, let's rewrite that. That's a right endpoint. Every one of these is the right side of our rectangle, not the left. So the area of each one of these rectangles is going to be that delta x for the base times the function value with the x value of the right side of the interval plugged in. So f sub of x sub I star. So this is a new notation maybe for us. Delta x, that is the spacing between the x values, and this f of x star sub I. Let me explain that for a second. The star is what's going to tell you how your rectangles are calculated. Are we using a right endpoint, like in this picture, or were we using a left endpoint, which our rectangles would have looked different if we had used a left endpoint, or is it a midpoint? So I encourage you to read about all three of those different options in the textbook. I'm just going to demonstrate the right endpoint here. So the star tells you which endpoint your rectangles are used by. And then the x sub I, this is a way to make a list of sequential values. So x sub I, this is what gives us our x sub 1, x sub 2, x sub 3, etc. The I is an index that can be 1, 2, 3, 4, 5, or 6 in our situation. We went all the way up to x sub 6. So it's a shorthand notation here. One rectangle will have this area. So one rectangle will have this area. But then to find the sum of all rectangles, we're going to use that summation notation that you may have seen in pre-calc, or if you read the chapter, you'll see it in there as well. And we're going to sum over all the values of I that we have. So that starts at 1 and it stops at 6. And we're going to add up each area, so the area from each one of these rectangles. So that delta x times f at x I star. So if we had an actual function and an actual interval, we would be able to calculate an approximate area. So this is not an exact area, because if you look very closely, you can see that there is some overestimation. These rectangles went above our curve. And then there's some underestimation here. So it's not a perfect answer, but it's not too bad. And in fact, the smaller or skinnier we make these rectangles that we've drawn, the approximation gets better and better. And that's one of the big ideas in integration, is that we can take this approximate area and we can turn it into the exact answer by allowing the number of divisions that we make on the x-axis, we let that get really large. So let's think of it this way. If I were to index from 1 up to some number n of the areas, delta x times f of xi star, if n were to go to infinity, that would mean I would have infinitely many rectangles in my picture. They would be infinitely thin, which means they would fit perfectly underneath our function. There would be no rectangles that go above the function, no rectangles that go below the function. So this would give us the true exact answer. And so this is the idea of approximating areas under the curve, that we can divide our area up into rectangles and add the areas of all the rectangles that we've created and call that an approximation for the area under the curve.